Today we're doing the sixth set of notes in the quadratics chapter. So if a quadratic equation does not have a b term, then you're going to use the square root method to solve. So the past couple days we have talked about factoring. Now we're going to switch gears and talk about this new method. So notice for letter A, I have an a term and I have a c term and I'm missing my b. So we are not going to use factoring. Instead, I'm going to introduce this new method. It probably will look familiar from geometry when you did Pythagorean theorem. So to get x squared by itself as much as possible, my first move will be to add the 9 over. And now I have x squared equals 9. And to get x squared by itself, I'm going to take the square root of both sides. And the square root of 9 is a perfect square. The square root of 9 will be 3. Now, a new concept that we need to discuss is that whenever there is a squared involved, that means I need to have two answers. So I'm going to put a plus or minus in front of my 3. The reason we do that is, well, 3 times 3 equals 9, but negative 3 times negative 3 also equals 9. So there's two results that would work, and that's why we always will put a plus or minus whenever we introduce a square root into the problem. Letter B, my first move will be to add that 38 over. When I do that, I get 2x squared equals 50. Then we're going to divide both sides by 2, and I get x squared equals 25. Again, to get rid of that squared, I'm going to introduce a square root into the problem. And when I take the square root of 25, we get plus or minus 5. The last type that is also going to be used for the square root method is something that looks very similar to vertex form. So when problems look like this, I'm not going to multiply them out by foiling or boxing. Instead, I'm going to keep it in this form, and my first move is going to be to divide both sides by 2. I now have x minus 5, the quantity squared, and it's equal to 49. Now that that quantity is by itself, I can take the square root of both sides, and when I do that, I'm left with x minus 5 on the left-hand side. On the right-hand side, I get plus or minus 7. Again, I put the square root there, so I have to put the plus or minus. And now I'm adding 5 over. Be careful, because I'm adding 5 to two different answers. I'm doing 7 plus 5, and I'm doing a negative 7 plus 5. So one answer is 12. The other answer is going to be negative 2. So the common mistake is that students will write plus or minus 12. I'm adding 5 to two completely different numbers. So now you have 3 practice problems to try. So the next thing that we have to discuss is two properties. So you're going to notice the past problems that we just did, they all worked out to be perfect squares. So now we're going to discuss, well, what happens if they're not perfect squares? So the product property says if I have two numbers underneath square roots that are being multiplied, I can put them underneath one square root and multiply the two numbers together. This property goes both directions, meaning I can multiply the numbers and put them together, or I can split them apart. Same goes for quotient. If I have two numbers that are being divided, I can write it as one big fraction underneath the square root. And again, it goes both directions, meaning I can pull them apart or I can put them together. So across the bottom of your screen, I just wrote your perfect squares. So if you don't know your perfect squares, you should jot these down in your notes somewhere. You can put them in the column going down the side of your notes. So the way we obtain our perfect squares is I take each number and I raise them to the second power. So I would do 1 squared is 1, 2 squared is 4, 3 squared is 9, and so forth. So that's where we got that list. We're going to be using that list today when we try and break down perfect squares. So you're going to notice the next section we're not solving. We're just going to discuss how to simplify square roots when they are not perfect squares. So the first example in this section says the square root of 18. And 18 is not perfect, but I can break down 18 to use a perfect square. So instead of 18, I'm going to say that 18 is the same thing as 9 times 2. 3 times 6 is also the same thing as 18, but the problem is 3 nor 6 is on my list of perfect squares. I always need to pick a number that comes from that list of perfect squares. Now that I changed it to be 9 times 2, I'm now going to give them each, their own square root. So I pulled them apart, they each get their own square root. And now I simplify. So the square root of 9 becomes a regular old 3, and I can't take the square root of 2, so the 2 stays under. So the 3 came out because that was the square root of 9. And that's my final answer. You do not have to put the plus or minus in front because the square root was already there. Number 5, my first move is to multiply these two together, and I get the square root of 20. But now I need to break it down because 20 does break down. 2 and 10 did not work. I couldn't break down 2. I couldn't break down 10. The other combination I want to focus on is 4 and 5. And the square root of 4 becomes a regular old 2, and the square root of 5 stays under. And as you feel more comfortable with these, you might be able to start doing some of these in your head. The last one we're going to talk about in this section is the dividing case. So again, the first move is to give them each their own square root. So I'm going to say the square root of 9 over the square root of 5. And now I want to simplify from here. So the square root of 9 is 3, and the square root of 5 is in the bottom. There's this unwritten rule in math that says you can't leave a square root in the denominator. So to handle it or simplify it, get rid of it, I'm going to multiply top and bottom by whatever square root is in the denominator. I need to do it to the top and the bottom to keep things the same. This is called rationalizing. So if you ever hear me say you need to rationalize your answer, this is what I'm referring to. Now when I multiply in my numerators, I cannot multiply the 3 and the 5 because 3 is outside and 5 is underneath the square root. So that's just going to stay 3 root 5. In the denominator, the square root of 5 times the square root of 5 is the square root of 25. And you're probably saying, well, I still have a square root in the bottom. How did this help me? But by doing this, I created a perfect square. And the square root of 25 is going to bump me down to 5. This is always going to happen. So if you can kind of recognize the shortcut, that whenever I multiply two numbers that are the same underneath the square roots are essentially going to just cancel. So that's how we handle rationalizing. So now I would like to go back and practice solving with values that are not perfect squares. So for number 7, my first move is to subtract 1 from both sides, and I get x squared equals 12. And again, now at this point, x is by itself, so I square root both sides. And I need to break down 12. So a modification, so you're not writing as much, is to make just like a little tree off to the side. To break down 12, the combination I want to use is 4 and 3, because I need to have one of them to be a perfect square. Plus or minus is coming back now. Because I introduced the square root into the problem and we are solving, I need to put a plus or minus. So I put my plus or minus there. The square root of 4 becomes 2, and the 3 stays under. Number 8, my first move is to add the 4 over. And I get x squared equals, and you know what, I realized I copied that wrong. I got ahead of myself. This should have said 14. So I'm adding the 4 over, and now I get 18. I was just predicting the future. So to get rid of the squared, I'm now going to square root both sides. Again, I'm going to put the plus or minus there because I took the square root, so I need two answers. When I look at 18, I want to break 18 down. The perfect square I need to use would be, again, a 9 and a 2. The square root of 9 is 3. The 2 stays under. One more example for today to wrap up on these notes. Again, this is very similar to what we call vertex form. I want to leave it in this form. I need to get the parentheses by themselves, so I will divide the 2 over. And I get x minus 5, the quantity squared. equals 6. And now from here, we square root both sides. On the left side, I'm left with x minus 5. On the right-hand side, I did take the square root, so I'm going to put a plus or minus. 6 does not break down. So sometimes numbers do break down, but not every number does. So 6 only breaks down to be 3 and 2, but neither one of those are perfect. So I can't go any further. I'm going to leave it at the square root of 6. And the last thing I need to do is add the 5 over. So I get x equals 5 plus or minus the square root of 6. The other way you could write it is the square root of 6 plus or minus the square root of 6 plus 5. So I don't care either way how you write it, just make sure the plus or minus is on the square root of the 6. And that's all for today.